So this is the solution to the concentration of reactant within a non-isothermal batch reactor. So to begin, we defined our time and time step. We set our Tmin equal to 0, our Tmax equal to 5, and our time step equal to 0.1 hours. Next, we plugged in our initial conditions. The initial condition of concentration was 1, and the initial condition of temperature was 16. We come down here below the, no need to edit below here, and created a segment for the number of times, or the time values between our time min and our time max, which is solved, created by Tmax minus Tmin divided by our time step. So next we created a variable TV, which we'll use pretty much later in the code to solve for the different steps in the Euler and predictor corrector method. So that was using a for loop from 1 to the segment that we created above, plus 1, and we created the vector TV of I, which was equal to I minus 1 times Tmax minus Tmin divided by the segment, again, which would be solved for up here. So next we programmed the Euler method. We made sure to note the initial condition, y Euler of 1 is equal to the initial condition of what we had earlier, and we created a for loop for I is equal to 1 to the length of TV minus 1, and using the provided Euler code we solved for the solution to the concentration curve using our dt, our initial condition, and a function that that's provided later in the script. So this section right here is for the Euler. This section down here was for the temperature. Then we, using the code provided, we created the predictor corrector curve. So again, we put in the initial condition, used a for loop to show that we want this to run for a certain number of times, and we plugged in into the code, our TV vector, our dt, and this f function, which appeared once again. That f function is right here. It is just the differential equation plugged into a user-defined function. So this is the differential equation for the concentration. This is the differential equation for temperature. So we go back up. You see here's f of a. This is concentration. This is temperature. So both of these methods create a vector of y values, ye of a, concentration, temperature, and ypc of a, concentration, temperature. Using these values, these are the answer pretty much to the differential equation once you use each method. And yeah, so you bring these down and then you want to plot them. So in this example we did a subplot. We plotted the concentration using the Euler method and the Y predictor method, gave it different symbols, X label, Y label, legend, title, and then in the second subplot we did temperature, did the same thing. And then we wanted to compute the error. So we found the differences between the Euler method and the predictor corrector method, took the absolute value. So here's concentration, here's temperature, and we again did a subplot and plotted the error between the Euler method and predictor corrector method versus time. Here's TV, which is our time. Here's the difference of the two methods. And plotted them and did the same thing for temperature and got two plots for that, which will be shown later. So the second part of this problem is we wanted to find the delta T required to get a certain level of accuracy. So here's that code. We used a while loop, brought down the y Euler and y predictor corrector method to solve for the values, and we wanted to find the mean difference between all the points. So we would take the same difference, but then this time we would divide it by the predictor corrector method as described in the problem statement, and set this equal to a vector called E. So E is the value of all these points. So E1 is equal to the mean of the difference divided by y piece E of A. And this changes as you run the while loop more times. Here delta t, or dt is equal to delta t, and delta t is defined up here. So as this while loop runs through, as delta t gets smaller and smaller, this delta t vector gets larger and larger with more values of delta t, until we get to a certain stopping point when E is equal or less than 0.01, which is dictated in the problem statement. So lastly, we wanted to display the required dt when we're finished, and then we've plotted the values of E as dt changes on a plot. So that is our solution to solving the concentration of the reactor and the temperature of the reactor over time.
Okay, so after we used MATLAB to code our graphs, we can now look at the figures that it plotted. And the first one is the concentration as it decays with time. So it starts out with all the reactant inside the container, and then it decreases as the reactant has been consumed. And this is plotted using the Euler method and the predictor corrector method. So they're not exactly the same. So we can compare those using the error, which we did in a later portion. Additionally, as the reaction took place, the temperature increased, and we can see that here. So this is a exothermic reaction. So it's giving off heat to a certain point, and then at the bottom here where there's not much of the initial reactant left, the temperature hits its maximum and then decreases as the reaction stabilizes. Our second graph was looking at the error and how that changed. So we can see that initially the error increased to its maximum for the concentration plot. At about 1 second it reached its maximum, and then after that, when we got further into the reaction, then the error between the Euler method and the predictor corrector method decreased, and then eventually at 0.01 is when we told it to stop. So that's why this stops down here, and that's 0.001, I believe. Then for the error in the temperature graphs between the Euler and predictor method, we see a similar trend because they're both evaluating using the same method. So the error occurs at the same time period at around 1 second. We get this maximum, and then further away from the initial time, it decreases with this slope. And then our final graph was the decrease of the delta t, the change in time, in order to figure out the average error. So kind of like the other graphs we were looking at, the average error increased to a certain point, and then decreased as time went on, and we decided that we wanted this to stop at 10 to the minus second, which is exactly what this point right here corresponds to.